Hi, and welcome to this context bite which aims to briefly describe the benefits of thinking about thermodynamics from both a classical and a statistical mechanics point of view. This course will only cover certain aspects of both perspectives, but hopefully this will enable you to see why thermodynamics is important to our everyday lives. So firstly, I should explain what I mean by the terms classical and statistical thermodynamics. Classical mechanics was devised in the 18th century fundamentally to understand how steam engines worked and to determine how to make them more efficient. There are a number of scientists that you will no doubt have heard of who were interested in the application of this new steam power to industry. Joule, Watt, Carnot, Clausius, Thomson, later Lord Kelvin, to name just a few dead white men. All laws and equations in classical thermodynamics are based upon macroscopic observations. People looked at the system, made a change, and noted the effect of that change. Everything is derived from empirical observation. Statistical thermodynamics, on the other hand, is entirely based upon the average, or statistical probabilities, of individual atoms or molecules. This method was developed by Ludwig Boltzmann before atoms were conclusively proven to exist. This microscopic atoms-up approach helps us to understand exactly what is going on in our macroscopic classical observations. But if it's not observation, then what underpins statistical thermodynamics? What are the fundamental concepts on which it is derived? The most important thing to consider in statistical thermodynamics is the energy levels within molecules. There are a number of different types of energy levels within molecules, and each of these energy levels are quantized, each with a different size step between the levels. The energy levels with the biggest energy gaps are electronic energy levels. Those with the next biggest energy gaps are vibrational levels, followed by rotational energy levels, and finally translational energy levels, which are so close together they can effectively be described as a continuum in most circumstances. You will learn more about the different types of energy level and how the energy values of these are related to molecular properties in other chemistry courses. But for now, knowing that these energy levels exist is all that is required to start to understand the basics of statistical thermodynamics. The statistical approach is then used to describe and justify some of our classical observations, but an extensive discussion of statistical thermodynamics is not the focus of this course. Since we are looking at things from two perspectives, the bulk and the molecular, we will see two different constants that do the same thing. One, R, the gas constant, which is used on the bulk level with the unit of joules per Kelvin per mole, and the other, Kb, which sometimes appears as just K, with the unit joules per Kelvin, which considers things on the molecular level, one molecule at a time. In fact, R, the gas constant, is Kb, the Boltzmann constant, multiplied by Na, Avogadro's number. When multiplied by temperature, these constants give us a thermal energy, and these constants are interchangeable in calculations and just affect the unit of the answer. I hope that this short video has provided a small amount of context as to why I am interested in covering some aspects of both classical and statistical thermodynamics. Thank you for listening, and if you have any questions, please do not hesitate to contact me.